Yeah, no, I gotta be a buzzkill, I don't care. Anyway, alrighty, so let's go ahead and finish up lesson 9. 2.9, yeah, logarithms. It's a quick lesson. We'll finish quickly because it's easy peasy stuff. Yesterday we talked about logarithms and what they do. We said that logarithms' job is to cancel exponential bases, right? As long as the exponential base matches the logarithmic base, they can perform their job. Great. What that means is you can only do log base 2 of 32 by hand if the argument 32 is a power of 2. Lucky for us, 32 is a power of 2. 32 is 2 to the 5th power. Log base 2 comes through, cancels exponential base 2, leaving you with just the 5. So there it is. Now, is 7 a power of 49? Well, technically, yes, it is. What relationship did the numbers 49 and 7 have with each other? 7 times 7. Basically, 49 is 7 squared. So then 7 is the square root of 49. And the square root is an exponent. So we can write this 7, instead of saying it is 7, we could say that it's 6. No, we could say that it is the square root of 49. Like that. So then log base 49 cancels exponential base 49, and you're left with the value of 1/2. There. All right, the next one. Yeah, this base is a fraction. I get it. But let's just not talk about that for a quick second. 4 and 64 share a common exponential base. Actually, they share 2 common exponential bases, but it's easier to go with the bigger one. As it turns out, 64 is a power of 4. So what I'm going to do is I'm going to teach you a trick that I will be able to show you. You've probably already learned the trick. I'll be able to show you why the trick is true later in our log notes. Not today, but in another lesson. For now, we're going to do it like this. Since you have identified that the base and the argument share a common exponential base, and for this one, the common exponential base is 4, or 2, whichever you prefer, but go with the bigger. They're both powers of 4. Write both the argument and the base of the logarithm as powers of 4. 64 is 4 to the 3rd. So 1 over 64 is 4 to the negative 3. The argument, 4, is 4 to the 1st power. This is how the trick works. Log base 4 cancels exponential base 4, leaving you with a fraction, negative 1/3. Is that actually how you evaluate this? No, that's not actually how you evaluate it. The way you actually evaluate it is you say that 4 is the, so it's like the cube root, the negative cube root. How do we say this? I'm saying this all kinds of wrong. It's 64 raised to the 1/3. So if you want it to look like that, you have to do it. This is 64 raised to the negative 1/3 or something like that. It's too difficult to even think about it, and as far as I'm concerned, when you could just ask yourself, what would I have to do to make this become a 4? Well, I would need to have a negative exponent. If I have a negative exponent on this 1 over 64, it's like the negative 1 power. That would give me 64. And how do I make a 64 become a 3? Cube root. There's the negative, there's the cube root. But this is a trick that you can use. In fact, we could have used it here. So now that we've talked about it, let's go ahead and use it again here. Instead of saying log base 49, I meant to grab my black pen, I can say these two are both powers of 7, where 49 is 7 squared, and the argument is 7 to the 1st, leaving me the 1 and the 2, so 1 over 2. That's a trick. It's only true because of a property of logarithms that we'll talk about in a future lesson. Yesterday we discussed the rules of the argument of the logarithm. What's the one rule about the argument of a logarithm? You guys remember from yesterday?
That it has to be greater. It has to be a positive.
Has to be a positive number or greater than 0. Since this argument is not greater than 0, this logarithm is undefined in the real number system. Can it be done with imaginary numbers and complex values? Yes, but that's not what we're doing. So it is undefined in the real number system. Not to mention, there's no way to raise a 5 to any power and get a negative result. That's impossible. 5 raised to every single number you can imagine will always result in a positive value. So, impossibilities. So remember what log says, what power of my base gets me my argument? Easy, right? Yes, Mr. Ram. Fantastic. So, let's get to the graphing calculator and its log base command. So if you don't have one, go grab one. Let's go, let's go, let's go. You pause the video while you're grabbing calculators. And now that we have our calculators, time to learn a command that is on them. These graphing calculators do have the log base command. It's a math structure, so it's in the math button commands. So you hit math, and then I just hit up, because it'll go to the bottom of the list. And at the bottom of the list, towards the bottom, you see log base. Enter, and there it is. And you just type the 3 in that box and the 15 in that box. It would be great if you knew that log base 3 of 15 has to be bigger than 2 but smaller than 3. Because 3 squared is 9, which is smaller than 15. 3 1/3 is 27, which is bigger than 15. So our value here is between 2 and 3. And there it is. I know the directions say to round to 4 decimals, but College Board wants 3 decimals, so I'm going to round to 3. 2.465. And then just do it again. Math up log base 4 of 58. Do I know what log base 4 of 58 equals? No, but what I do know is that 4 to the third is 16, smaller than 58. I said that wrong. 4 to the second is 16, smaller than 58. 4 to the third is 64, bigger than 58. My answer is somewhere between 2 and 3. Darn near 3, because that number was very close to 64, which is the third power of 4. So 2.929. Scoot it over. I actually have no idea how to estimate this like I was doing with the other ones. But I can tell you that I know that this value is going to be negative. But how do I know that? Because the base of this logarithm is between 0 and 1. And if you raise any number between 0 and 1 to a positive integer, your value gets smaller. But since I need it to get bigger, I can't use a positive value. I must be using a negative value. Think about it. Raise the number 1/2 to the second power, you get 1/4. 1/4 to the second power is 1/16. 1/16 to the second power is 1 over, what is that, 324? No. 16 squared? What just happened to my brain? 256, I'll be okay. But the point is, you notice how it got, what, Jackson?
I just wanted to tell you that if you do math and then alpha math, it brings you right there.
Okay, yeah, math, alpha, math. Okay.
I just wanted to tell you.
And how did you discover that?
I just saw it was A.
Oh, you mean you noticed that it's that. Got you. Because A is, it's like hitting 1 to go to the first one. Yeah. I don't know if that's faster. Let's see. So I said math, up, enter. So math, up, enters 4 commands. You did math, alpha, math. Ooh, shorter by 1 button click.
And you don't have to go all the way to the up button and then down to the enter button. You just go math.
Oh, he's trying to minimize the finger distances. Got you. That's good. Yeah. God forbid we lift a finger. Okay. Anyway.
You only have like an hour.
Wait. Math, alpha, math. Oh, look how fast that was. Thank you, Jackson. Okay. Anyway, 0.35 and 8.4. Negative value of some sort. Negative 2.027. And then the last one. 5 over 2 is a number larger than 1. So since this value is larger than 1, we're going to have to raise it to some kind of positive power to get up to 125. What power? I don't know. I do know that if there wasn't a 2 there, it would have been 5 to the third, and the answer would have been 3. So it's got to be bigger than 3, right? Because 5 over 2 is smaller than 5. So our answer has to be bigger than 3. Wait. Math, alpha math, my new favorite shortcut. 5 over 2, and
You're going to use that for the rest of your life.
I will probably forget it tonight, to be real with you. I'm going to go out of my way to forget it. I'm going to be like, what did that kid tell me?
It's just because he said it.
I'm going to spite him. I'm going to forget it. I will spite him. 2, 6, 9. You can actively forget things. Einstein did it all the time. Yeah. Actively forgot pop culture.
Wow.
What happened?
Someone said, wasn't Einstein smart though?
Yo, wasn't Einstein smart though? That's okay. I'm the one that controls the grades. We'll see who's laughing at the end.
Just like I should remember when you're putting in my grade, then I tell you a trick on the
Yeah, okay. So I'll remember Jackson in a positive light because of the trick on the calculator. Good. Alrighty. So let's talk about something called orders of magnitude. I guess that this is not a type of words that are used much anymore, saying something is orders of magnitude larger. But in case you've ever heard that statement, when you say something is an order of magnitude larger, it means 10 times more. So if you say 2 orders of magnitude larger, that's 100 times more. An order of magnitude means times 10. Alrighty, so use a calculator. We're going to compute these values. I am not going to compute all of the ones from log of 3 times 10 to the second to here. I'm just going to do all these 3 numbers. All right, I'm not trying to go crazy here. So let's do log of 3 times 10. Log of 3 times 10 is 1.477. I wonder what's going to happen when I do log of 3 times 10 squared. Let's see what I get. 2.477. It went up by 1. Exactly 1. You know, just to see if it was a fluke, I'm going to do log of 3 times 10 to the third real quick and just see what happens. Oh my gosh. 3.477. I wonder what that last one's going to be. Well, here's what I see. This number, actually, you know what? I don't want to spoil a surprise. Let's see. 10.477. So what is the pattern in the integer parts of these numbers? Looks to me like it's increasing by 1 each time. So what's the pattern in the decimal part? Hopefully it's obvious that it's staying the same. No change. I guess you could say that no change is technically a pattern. Okay. Interruption. It's past. It's gone. All right. Anyway, what was I saying? Oh yeah, looking at the numbers, seeing that there is no change in the decimal parts. Well, how many orders of magnitude greater was this number than this number? I'll tell you what. Let's talk about why this is happening. Every time we got another power of 10, our integer part went up by 1. The reason why is because this is the common log whose base is 10. And log base 10 of 10 equals 1. So every time there was another multiple of 10 in here, I got another addition of 1 here. This one has 9 more powers than this one. So this value is 9 more than this value. So how many orders of magnitude greater is it? 9 orders of magnitude. Side quest. People always want to know how logarithms are useful in the real world, right? Well, you already use them pretty commonly. I mean, not regularly, but commonly. For example, you talk about how loud your music is. That's decibels. Decibels are measures of pressure. They're on a logarithmic scale. The pH of a substance measures the acidity or basicness of a substance. It's logarithmic scaled. Light intensity, logarithmically scaled. Richter scale, logarithmically scaled. Things like that. So you use them commonly in your life, you just probably didn't know it. Yeah? Yes, Mr. Rapp? Fantastic. Oh, another interruption. Fantastic. Let me pause the video again. God, okay. Was that interruption 2? I didn't say bad anything about myself. Anyway, moving on. Or flip this. Someone's knocking on the door. You got effing kidding me right now. It's just someone coming back from the bathroom. Okay. Yeah, yeah. Thank Bob. I don't know how to edit these videos. I don't edit anything. Anyway, Richter scale. The intensity levels I of 2 earthquakes measured on a seismograph can be compared by the formula log of intensity 1 divided by intensity 2 equals m1 minus m2, where m's are the magnitudes on the Richter scale. Okay. How many times more severe was the 2001 earthquake in that place, India? I can't say that. Which was a magnitude 7.9, then the 1999 earthquake in Greece, I guess say Athens, but you know, which was a 5.9. So just how many times more severe? Basically what you're saying is how much more energy. Because that's what the Richter scale is actually telling you. The number on the Richter scale, it corresponds to a number of energy that was released by the Earth. So let's set it up. Log of I1 divided by I2, I like parentheses on my argument, is M1 minus M2. By the way, you do not have to have this memorized, this formula. This is just us using it, okay? Intensities, we don't know. Magnitudes, we do. It's actually kind of boring because it's a pretty number. M1 is 7.9, M2 is 5.9. Log of the ratio of intensities is 2. This is the common log. Its base is 10. Yes? Yes, great. So if you want to get rid of the logarithm, you need to use exponential base 10 of both sides. So we'll just throw a base 10 down there and a base 10 down there. On the left-hand side, exponential base 10 and log base 10 cancel. And what we'll be left with is a ratio of their intensities being the number 100. What that means is the magnitude 7.9 earthquake was 100 times more severe. And by severe, we mean 100 times more energy released than the magnitude 5.9. 100 times more severe. Or you could say 2 orders of magnitude. It means the same thing. 10 to the 2. It's actually pretty easy. Especially, you don't have to have the formula memorized, like I said. You just need to be able to use it. Last one, and we're finished. pH scale. The pH scale model. pH equals negative log of H plus. By the way, you do not have to have this memorized. You just need to be able to use it. pH equals negative log of H plus is a scale that measures how acidic or basic a substance ranks. The scale ranges from 0 to 14, where 7 represents neutral, and each whole pH value below 7 is 10 times more acidic than the next higher value. By the way, H plus is hydrogen ions. I guess they're positively charged. Okay. Balsamic vinegar, oh, an ant. Kill this bad boy. Get out of here. Balsamic vinegar has a pH of 2.4. And a box of baking soda has a pH of 8.4. What are their hydrogen ion concentrations? So for the vinegar, the pH, whoops, we know the pH, 2.4 is negative log of H plus. Divide both sides by negative 1. For some reason, chemists use brackets instead of parentheses there. I don't know why. They just do. And to get rid of the log, we're going to do the same thing we did last time. That is log base 10, so you use exponential base 10 to cancel that logarithm. And what you get is balsamic vinegar's hydrogen ion concentration is 10 to the negative 2.4. We don't need to type that on a calculator. That's just what it is. It's good enough. It's like scientific notation. And then the baking soda, which we will abbreviate as BS because it's funny, would be 8.4 equals negative log of H plus. Again, divide by -1. And then base 10 on both sides. Find out that baking soda's hydrogen ion concentration is 10 to the negative 8.4, whatever that means. Without scale, units, it's kind of tough to know what that means. But whatever, that's neither here nor there. Those are their hydrogen ion concentrations. How many times greater is the hydrogen ion concentration of the vinegar than the baking soda? Meaning how many orders of magnitude? This is a larger number because its exponent is closer to 0, right? So let's, what's a good color? I'm feeling green. Vinegar over baking soda is 10 to the negative 2.4 divided by 10 to the negative 8.4. And anytime you divide two numbers with the same base, you just subtract their exponents. Negative 2.4 is a bigger number than negative 8.4. How much bigger? 6. So this is 10 to the 6. So how many times greater is it? 6 orders of magnitude greater. Yeah, 1,000,000 times more hydrogen ion concentration. 6 orders of magnitude greater. And that is it in this comedy of ridiculousness.